Good morning, everybody. Hope you guys are doing all right. Let's get things going here. Here's the usual attendance form as well as a link to the tutoring. So if you want some tutoring help, it's available. I don't do that. She can make that work somehow. Excuse me. So I can do smart. And here it is again, just in case you want it. I just put a period at the bottom there, so there's more spacing between the things, so it's easier to differentiate between them. I'm aware the FAM people had a midterm. It was due last night, although I imagine some of you could still be working on it if you can turn it in late today. And yeah, it looked really great. So I know he's trying his best, but I imagine it's frustrating. So that said, yeah, I don't know what to say. I would say I was looking at the class yesterday, and it certainly seemed like some people got a little bit heated in the chat, and I would just try to not engage if it was me. So yeah, good times. All right, so here's what I want to say. Mercs and FAM are obviously diverging quite a bit, right? Mercs, you guys are way into this, doing things I didn't know you guys were going to be doing. Whereas FAM, you guys just started talking about iteration by parts. And so what I'm kind of thinking is, it's hard to help both classes during the same class time because you guys are just doing such different things. So what I think will be best for the rest of the quarter, which is the next 3.5 weeks, is for Tuesdays to focus mainly on what Merck's class is doing, and Thursdays to focus mainly on what FAM's class is doing. And then on Tuesday and Thursday afternoon, I have an office hour for my stat students, which none of them are coming to. But I can also open that up for you guys as well. So today it'll be actually, let me just make sure I know the time correctly. I think today it's 2:30. Let me double check on that real quick. Where are you? Sorry. I know I had you up somewhere. There we go. Yes, today I have office hours at 2:30, and then on Thursdays I have an office hour at 1. Sorry, today is Tuesday. I have an office hour at 2:30. On Thursday I have an office hour at 1:30. And any of you are welcome to come, but specifically, so there's the link to today's office hour. So today I think we should focus more on Merck's class, also because last week we focused a lot on FAM's class. So today we'll focus on Merck's. Anyone's welcome to the office hours this afternoon. Specifically the FAM people, if you don't get your questions answered or addressed today, we can or during class today, we can definitely come out of there. Talk about them in office hours this afternoon if you would like. And I feel like there was something else I wanted to say about that. And then Thursday we'll flip it up. So Thursday we will focus more on what FAM is doing, which I imagine will be mostly integration by parts still. And then Thursday afternoon I will have an office hour, and anyone is welcome to that as well. That said, everyone is welcome both days. And if people from that day's classes focus aren't asking many questions, we can go to the other people and see what they've got going on. So I think I've said all the things I want to say. Let me post up the attendance one more time. And the tutoring. Hopefully you guys are using the tutoring. I've heard some students tell me they have been using it and it's been very helpful. So I would encourage you to use the student tutors if you are looking for extra help. And once again, here is the Zoom office hour. It'll be happening today at 2:30. And if there's the password, if there's a password, it's Newton. So the password's always Newton. All right, I've said all the things I think I wanted to say. So let me ask you guys in Merck's class specifically, what do you want to talk about today? Are there things that the Merck's people would like to see? I have some ideas, but I want to hear if you have any specific things before I get going. Actually, I do have, I know someone asked me a specific question a while back that I kind of spaced on doing. So I'll start with that, which is a partial fractions problem. If I can find it. Where'd you go, partial fractions problem? Sorry, one sec. I really had it just a second ago. The quiz is optional for everyone. It's certainly, okay, converges there, yeah. Yeah, the quiz is optional for everyone. Nobody has to take the quiz. Certainly it is written with the people in Merckx's class in mind this week because it has topics the FAM class hasn't covered yet. So specifically for FAM students, the quiz is very optional. But even for those in Merckx's class, if you don't want to take it, don't have time to take it, you don't have to take it. I would like everybody to take it. Well, I would like everyone in Merckx's class to specifically take it. FAMS people, I don't really think you should take it unless you really know that material already. So that's what I would say. Okay, convergence, divergence, volume, cylindrical shell method, great, yeah. I didn't think he was going to cover shell method, but I guess he did. So, and we can totally talk about shell method. I like shell method, and I've got what I think is a good way for remembering when to use shell and when to use disk or washer. But it really, I literally was just looking at the example I wanted to do, and now it is gone from my brain. Sorry, it's gone from my, I have like a list here of things, of questions to do, and I can't find it anymore. Oh, there it is. I see it. All right, cool. So let's do this one. In fact, I can make this more interesting. So, yeah, I'm going to do two things at once here. Not just more interesting, more educational. So we want to find the integral of, make sure I'm not going to be totally stupid here. That should be fine. This might not turn out to be as great as I want it to be, but it'll be close. Let's do the integral from 5 to infinity. I might change that lower limit of integration in a minute. Of 2x over 6x squared minus x minus 7. Let's make that lower limit 8, just because I'm not convinced that, yeah. Okay. So a couple things here. One, clearly improper integral, right? We're going to have to use a limit to infinity at some point. And two, it definitely looks like it's a partial fractions kind of deal. And the way I can see that is, well, what else would you do, right? You could try you said it's not going to work. I can definitely see the degree on top is lower than the degree on the bottom, which is what I'm looking for. Those crickets are super loud. And I'm pretty sure that thing factors. So let's look at this factoring for a second. So 6x squared minus x minus 7. So this is where you have to kind of like, I'm just going to guess. The guessing seems terrible. And I have to have a 7 and a 1 here. And I'm trying to make it multiply out so it adds to like -1. So I think I want like a 6x and a 1x here. And I think I want a -7 and a +1. So that when I multiply it out, I get a -7x and a +6x, and that adds up to a -x. There are certainly other ways to factor things like this, but often you can kind of just guess and eventually figure it out. The hard part is when your coefficient here is something other than 1, you have to be more careful with making sure when you multiply out the middle terms, they add up to actually what you want the middle term to add up to. And this is how it works. So I'm going to do my partial fraction decomposition before I do anything. So I got 2x over 6x minus 7 times x minus 1 plus 1. I'm sorry. Oh, and here's the, I almost got my pen on the carpet. There's the, oh, that's not daytime. There's the Zoom office hours later for this afternoon at 2:30. And here is the attendance and tutoring link once again. And if someone else asks for it and I don't see it, someone else just throw it up there. So I got a over 6x minus 7 plus b over x plus 1. Someone asked about this integral before, but not with these limits of integration. So we'll do the integral and then we'll figure out how this improper part works. So multiplying both sides by the common denominator. On the left, I'm going to get 2x. On the right, I'm going to get a times x plus 1. And then b times 6x minus 7. We've got two convenient values of x. One of them, well, one of them is less convenient than the other. The nice one is x equal to -1. When I plug that in, I get -2 on the left. I get 0 times a, and I get b times, let's see, -6 minus 7 is -13. That might be looks terrible there. So then -2 divided by that, so b is going to be +2/13. And then plugging in x equals, okay, what's the value that's going to make 6x minus 7 equal to 0? X has to be some not lovely fraction. It's going to be 7/6. All right, I'm really just setting this equal to 0 and solving for x. So I'm going to plug that in. This is going to be real nice. So plugging in 7/6 here, I get 2 times 7/6 equal to a times 7/6 plus 1. All right, let's do some math. So 2 times 7/6 is 7/3, and 7/6 plus 6/6. Gosh, those words are not the easiest for me to say. 7/6 plus 6/6 sounds really good. Is 13/6. So then I'll multiply both sides by 6/13. Those cancel. 6 and 3 cancel. I'm left with 2 times 7 is 14/13. Lovely. So here's what we end up with. We end up with a being 14/13 over 6x minus 7. And b is, what was it, 2/13 over x plus 1. All right. So now we're going to do the integral. And I'm going to do the integral without the limits of integration. Because I think trying to, no. Yeah, let's just do that. So let's say, yeah. This might not turn out to be as excellent as I thought it was going to be. That's all right. So here's what we've got. We've got the integral from 8 to infinity of 2x over 6x squared minus x minus 7. Equal to the integral from 8 to infinity of this plus this. So 14/13 over 6x minus 7 plus 2/13 over x plus 1. All right, so we're going to take, we can, this is going to be the limit as x, sorry, not x, we can do something up. Any other letter would be fine. Limit as t goes to infinity of the integral from 8 to t of 14/13, 6x minus 7, 2/13 over x plus 1. All right, the x equal to, now we need to actually integrate these things. Integrating these things isn't hard though, or at least it's not that terrible, I should say. So, right, I'm just thinking this 14/13 is a coefficient. So I'm really thinking of this as 14/13 times 1 over 6x minus 7. And the integral of 1 over 6x minus 7 is the natural log of the absolute value of 6x minus 7 divided by 6. So I get, I know, it's not quite as nice as I'm trying to pretend it is. You get 14/13 times the natural log of the absolute value of 6x minus 7 divided by 6. Plus, same deal here, 2/13 times the integral of 1 over x plus 1 is the natural log of the absolute value of x plus 1. I don't need the plus c because it's definite. I have from 8 to t. All right, so let's take a look here. Plugging in t. Now this one actually is interesting. Okay, the limit as t goes to infinity. Let's see. Sure, I'm just gonna write this as 14 over 13 times 6 is 78 times the natural log of the absolute value of 6x minus 7. Oops, I'm plugging in the limit, sorry. I'm plugging in t. Minus, I'm plugging in 8. 14/13. 14/78, gross. Natural log of the absolute value of 6 times 8 is 48 minus 7 is 41 plus 2/13. Natural log of 8 plus 1 is 9. Okay, we're almost done. So then we say, okay, as t goes to infinity, what's happening to the natural log of 6t minus 7? Well, the insides are going to infinity, and when the insides go to infinity, here's the natural log function. As the, right, this is y equal to the natural log of x. As x gets bigger and bigger, the y values also get bigger. So if the insides are going to infinity, the whole thing's going to infinity. So this goes to infinity. Ow, son of a gun. It didn't actually hurt that much. It just, you know, when you think you're going to hurt yourself and you say ow, even though it doesn't really hurt. It didn't hurt that much. This is also going to infinity because the insides are going to infinity. If this was subtraction, we'd have to work harder because we have the indeterminate form. But since it's an infinity plus an infinity, this whole piece goes to infinity. So you get infinity minus some number that's just a constant. Infinity minus any non-infinite thing is still, I suppose, infinity minus any finite thing, which is a better word for non-infinite, is going to be infinite. So this one diverges to infinity. And I just want to point out, in general, we know that the integral from 1 to infinity of 1 over x diverges. And this is essentially, although it's not exactly the same, it's the same enough, right? The difference in degrees, the top is a degree 1, the bottom is a degree 2. The difference is 1, so the bottom is 1 bigger. The bottom degree is 1 bigger than the top degree, and you're going to infinity, you almost always get divergence because you get a natural log of something, and that's going to go to infinity. Okay, that was a good problem. So let's look at some more. Let's see. So we've got convergence to divergence and volumes of cylindrical shells. Okay, let me do another convergence divergence problem, and then we'll talk about some shell method stuff. Okay. So let's see here. Let me think here for 1 second. Yeah. So the other kind of so there's 2 types of improper intervals that we usually encounter. One's where you have, right, an integral with an infinity or a negative infinity. That's always going to be improper. But then there's the other kinds where the integrand, the function you're integrating, is undefined somewhere over the interval of integration. Also, here's the attendance and the tutoring again. So we could have something like, let's see, sure. Let's do something like this. The integral from, sure, 1 to, so I'm trying to think of something somewhat clever. Sorry, let me think for 1 second. 1 over the square root of, sure, fine. Sure, there we go. The integral from 1 to 26 of 1 over the square root of x minus 1. And this integral, or I should say this integrand, is clearly undefined where? Where is this definitely for sure undefined? Definitely. And even more generally, it's actually defined everywhere where x is less than or equal to 1, right? Because if you plugged in negative, or if you plugged in like, you know, anything less than 1, you're going to have a square root of a negative number. Those numbers we don't really care about in this instance because we're starting at 1, but it is good to be aware that, oh yeah, this is actually undefined everywhere less than 1, less than or equal to 1. So since it's undefined at 1, we're going to rewrite this as the limit as a approaches 1 of the integral from a to 26 of 1 over the square root of x minus 1 dx. And although this is probably perfectly fine, technically I'm doing it slightly wrong. Really, I should be saying I'm approaching 1 from which side? Should I be doing the limit as a goes to 1 from the right, or as a goes to 1 from the left? Which side of 1 am I on? You guys can write a plus or a minus sign. or you can say right or left. So if you're not sure, think about the fact that we're between 1 and 26. So if I write it on the number line, here's 1, here's 26, I'm in here. So which side of 1 am I on? I'm on the right side of 1. So that means I'm on this side. And it's always going to be true that if it's the lower one, you're always going to be approaching from the right. If it's the upper one, you're always going to be approaching from the left. And it's not that big a deal, but it should be written because it's technically incorrect if you don't write it that way. And I could see a teacher being nitpicky about it. Okay, so now we're going to integrate. You can either, well, in fact, let's actually rewrite this. Actually, let me do this. Let me pretend like I was smart enough to do it here and rewrite this as x minus 1 to the negative 1/2. And although you could do a u sub here, you could totally let u equal x minus 1, du would be dx. So then you'd just be integrating u to the negative 1/2. I don't think we really have to actually do the u sub. We can say, okay. I mean, I'm happy to do it if you guys want me to, let me know. But I think it's okay just to say, all right, the integral of u to the negative 1/2 is u to the positive 1/2 divided by positive 1/2. But our u was x minus 1. Now, of course, dividing by 1/2 is really multiplying by 2. So really, I would say it's x minus 1 to the 1/2 times 2 instead of divided by 1/2. And then we're going to plug in our limits of integration. I will say for these types of integrals where it's improper, I generally prefer not to change my limits of integration if I'm doing a u substitution, which is why I kind of avoided actually doing the u sub. The limit as a goes to 1 from the right of 2 times 26 minus 1 to the 1/2 minus 2 times a minus 1 to the 1/2. 26 minus 1 is 25. 25 to the 1/2 is the square root of 25, which is 5. So I end up with 2 times 5 minus, when I plug in 1, I get 2 times 0 to the 1/2. And what's 0 to the 1/2 power? Yep, that's right. It's ding dong. Everybody knows 0 to the 1/2 is 0, right? Because 0 to any positive power is going to be 0, right? Just the square root is 0. So I end up with just 10, which means this one converges to 10. And that's how we would do that one. I know I said only one more, but I want to do one more really, and then we'll do some cylindrical shells. Sorry, there's just one more thing I keep trying to say. So let's look at, let's see, what's a good example? Yeah. That's interesting. Okay. All right, here's another improper integral. Let's do that. Let's do the integral from, I was going with the same example. Let me try something a little bit different. Yeah, we should do one of those. Okay. Sure. From 3 to 10 of 1/4 over x minus 5 to the 3rd. Sure, that doesn't seem too incredibly awful, I guess. All right. First things first, the 10. Where is this undefined? Gosh, my hair looks really crazy today. Yeah, 5. Also, just in general, something to be aware of on maybe your next midterm or your final. I could see asking a question like this and not specifically saying it is one where you have to use right where it's improper. So I could see like there being a section of definite integrals on your test, and having one question like this and one question like, I don't know, let's make something up like, I don't know, let's make something not stupid, James. Something like this. This one is not improper, right? This function is never undefined, so you would just do a u sub and integrate it normally. Whereas this one is improper, but you have to pay attention to know it's improper, right? If you're just looking at these, you might kind of forget that, oh, this is undefined at 5. And 5 is in between those. I should also point out this integral is also not improper because the function is not undefined over the interval. So these ones you would just integrate normally. This one you have to actually deal with the problem point of 5. So be careful, right? If you see a section of definite integrals on an exam and you see a function that might be undefined somewhere, make sure that if it's undefined, you have to check and see, is that undefined point between the limits of integration or one of the endpoints of your limits of integration? I mean, it's a weird like flashing thing happening. So yeah, just something to be aware of. So we're going to break this up. So when the point's not on one of the endpoints, it kind of sucks extra. You have to do it, from 3 to 5, to 4. Let's write it how I actually want to write it, which is 4 times x minus 5 to the negative third, plus the integral from 5 to 10 of 4 times x minus 5. Right? We have to break it up at the point where it's undefined. And then we have to do each of these integrals on their own. So let's deal with, let's see which one do I want to do. Doesn't really matter, I just want to make it. So let's do this one to kind of display it. So typically when there's 2 pieces or more, you just have to do each one separately. And we're going to just do them piece by piece. So let's do this one first. So let's see, I'm going to write this as the limit as b approaches 5 from the left side, because if I'm between 3 and 5, I'm definitely less than 5, which is the left side of 5, of the integral from 3 to b of 4 times x minus 5 to the negative third equals. All right, so then I think this board's a little too close to this table here. I'm going to scoot this in over to the right a little bit. Do that later. So this limit is b goes to 5 from the left. I'm going to integrate this. I'm just using, or I could do a u sub for u equal to x minus 5. I'm going to say it's my integral is 4 times my u minus 3 plus 1 is minus 2 divided by minus 2 from 3 to b. And that u was minus 5. And so this is looking like the limit as b approaches 5 from the left. I like to simplify this. Well, we can plug in. So I'm going to have 4 divided by negative 2 is negative 2. So negative 2 times b minus 5 to the negative 2 minus negative 2 times 3 minus 5 to the negative 2. Okay, now here's where we have to be extra careful. When I plug in 5, I get 5 minus 5, which is 0. This is equal to negative 2 times 0 to the minus 2 plus 2 times negative 2 to the minus 2. And this is where I often see a mistake. What's the deal with this 0 to the minus 2 here? Anyone want to chime in and tell me what they think that might be? Well, I spit water all over the place. Sorry. All right, what's 0 to the negative 2? Definitely, yeah. But it's definitely a place where it's easy to make a mistake. Right? So 0 to the negative 2, that's undefined because we really have division by 0. So undefined, which means this whole thing diverges. And now here's the nice thing about this. We didn't even look at the second piece, and we don't have to look at the second piece. Once one piece diverges, whether it's to infinity or negative infinity, I'm not even going to check, because when one piece diverges, the whole thing diverges, and we don't really know if the whole thing diverges to some sort of infinity or something else. So we just get to say this diverges. We do not have to look at the other piece at all, which is great. Okay. Are there questions about this? Also, here is the attendance and the tutoring again. All right, seeing no questions, let's move on and start talking about some cylindrical shells. Okay. Again, for those of you that might have joined us late, I've decided that on Tuesdays we're going to focus more on what Merck's is doing. Thursdays we're going to focus more on what FAM is doing. So if you're in FAM's class today, you're certainly welcome to attend. But we're covering stuff. We've been covering improper integrals, and we're going to be covering now some volumes by shell method, which I really imagine FAM will not cover. So you're certainly welcome to stay, but you do not have to be here if you find the material is not particularly helpful to you. Totally understand if you're like, I don't really need to see this. All right, so shell method. So sure, fine. So I want to find the volume of the solid contained by revolving. Sorry, these ones are always so long to write out. The region. Let's start off with a not too terrible one, James. The region bounded by y equal to the square root of x, y equal to 3, and x equal to 0 around the y-axis. And we'll actually probably do this using both methods, just so you guys can see that both methods will work, and it really just kind of depends on how you want to think about it. As usual, I would highly, highly, highly recommend graphing the region. So, and I think it's perfectly fine to use a graphing utility if you want to. So you can use Desmos, y equals root x is going to look like this. And then y equals 3 is going to look like this. And eventually they're going to cross, right? They're going to cross somewhere here. And then x equals 0 is going to look like this. So I'm looking at this region here. And you can either, if you're using a graphing utility, you can just kind of scroll over to where they intersect and see that it's at x equals 9. Or you could set y equals 3 and y equals root x equal to each other. And when you set 3 equal to root x and square both sides, you get x equal to 9. So this point here is the point 9, 3. And we're going around the y-axis. Okay, so here's the thing to remember. And actually, this is one of the reasons why I generally emphasize that for the disc or washer method, the strip that I'm thinking about drawing is perpendicular to the axis of rotation. So if I was using the disc or washer method, I would draw a perpendicular strip, so a horizontal strip, and think about it revolving around the axis so that I get a disc. With the shell method, it's the opposite of that. So instead of drawing a strip that is perpendicular, I draw a strip that is parallel to my axis of rotation. So since my axis of rotation is vertical, I'm going to draw a vertical strip. And here's the thing I always like to say. Shell rhymes with parallel. So when I'm doing the shell method, I'm always drawing a strip that is parallel to my axis of rotation. And then this strip is going to rotate around the axis, and it's going to give me a cylindrical shell. So here's what this is going to look like. So let's kind of do this down here like this. And then we'll try and do this like that. Yeah. So there is your cylindrical shell, right? And literally the words describe what it is. It is the shell of a cylinder. And the volume of this shell, well, what people usually think about doing is they think about cutting this shell. I'm going to cut it like right here. And I'm going to unroll it. So like I'm going to be like, maybe I should cut it over here. So you'll be like, unroll. And it's going to unroll to being something that looks like this. And yeah, there's a little bit of curviness at the end, but again, it's kind of an approximation, so we're not going to sweat it. I'm going to roll it, and the height here is the same as the height here. The thickness, which is a small change in x, right? The thickness is a dx. That's going to be this thickness here. And the length of this is the length around, which is the circumference of the circle. So that's going to be 2 pi r, where a couple things. So we're imagining this strip is at a distance of x from the axis of rotation. Because we're going to let x go from 0 to 9. So this strip is located at x, so that radius, that is x, because that's how far from the axis of rotation is, right? This looks like, that's our radius. And then this height is just the height of the strip, which is either going to be, well, no, it's going to be the difference in the function. So it's going to be the top function minus the bottom function. So this height here, which let's just do it this way, that height, that's going to be the top minus the bottom. All right, so let me erase some of this so I can write what I want to write here. So I think I can erase the phrasing of this because we've got the picture that kind of covers it. So here's what I'm saying the volume of our shell is. And this is how I always start. The volume of my shell is 2 pi r times h times d x in this case, because it's a vertical strip. So then that's 2 pi times x is my radius, and my height is the top function, y equals 3, minus the bottom function, y equals the square root of x. So that is the volume of my shell. And then I'm going to quote unquote add up all the shells by integrating. I'm going to integrate from 0 to 9. There's probably some good pictures in the book. Maybe I'll take that back. Let's take a look in the book for just 1 second so I can kind of, you know what? There's not good pictures in this book because the book doesn't cover shell method. There's good pictures in this other book. So let me try and show you a picture real quick just so I can kind of give you an idea of what I'm trying to say. Maybe I'll look for better pictures later. Sorry, volumes. Oh, where are you? Sorry, 1 second. Volumes, page 374. Cool, yeah, so hopefully you guys can see this picture all right. Maybe, sorry, I might have trouble seeing. So there's the idea there of the shell thing that I'm doing, where I'm taking that cylinder and then unrolling it to look like kind of a big rectangle. And then the idea is that, hopefully there's a picture of what I want on the next page. Yeah, this book does not have the pictures I was hoping for. Do I have my other book? I do. Let me look at my other book. Sorry, I know I'm kind of, no, I think it's good to see this picture. That's not the book I want. Shoot. Don't have the other book. Oh well. So what I was going to try and say is, basically you've got all these shells kind of stacked around each other. So like in the middle, you have this kind of very thin shell. And then when you move out, right, you're gonna have a shell that is not quite as tall. So it's gonna be like a shell that's gonna be like, and please forgive my drawing, it's gonna look terrible. But you're gonna have a shell that's kind of like this, but it's gonna be right not as tall. So it's gonna be kind of like that. Right, where it goes behind this other one. And then as I draw as I have further and further out shells, they're gonna still have the same top with the top of this. Right, we're going to be like kind of like that. And here's another shell that's going to be a little bit shorter, right? So it's going to be like that, like that. And so I'm just adding up these shells on top of each other, or actually surrounding each other. But the idea is that quote unquote adding up is just the integrating part. So the total volume is going to be the integral from these shells start at 0, these shells end at x equal to 9 of this mess here. 2 pi times x times 3 minus the square root of x, which is x to the 1/2. Okay, before we continue, are there questions? My shake is starting to warm up. Hopefully it's not too dark. I feel like it's too dark. All right, no questions. So for this one, it's different than the washer method or disk method, right? You're not squaring both things. You just have to have, you're going to have x or y on the x-axis times your difference in function heights. So we have to multiply this out. So we get 2 pi integral from 0 to 9 of x times 3 is 3x, and x to the first times x to the 1/2 is x to the 1 plus 1/2, which is x to the 3/2. And then we're going to integrate it as usual. 2 pi integral from 0. Sorry, I'm actually integrating it. I don't write the integral anymore. I'm integrating it. Integral of 3x is 3x squared over 2 minus the integral of x to the 3/2 is x to the 3/2 plus 1 is 5/2. Divided by 5/2 is the same as multiplied by 2/5 from 0 to 9. All right, and let me go ahead and just give myself a little more room here. Sorry. Plug in 9, I get 3 times 9 squared over 2 minus 2 times 9 to the 5/2 over 5 minus 0. Right? When I plug in 0, I get 0 squared and 0 to the 5/2 equals 0. And then we could simplify that. We could not. The simplifying here is not the important part. Although I guess I should point out 3 times 9 squared. 9 squared is 81. 81 times 3, well, 80 times 3 is 240. That's 1 times 3 is 3. I get a 243 over 2 minus 2 times 9 to the 5/2 is also 243 because the 9 to the 1/2 is 3. And then 3 to the 5th is just 3 to the 4th, which is 81 times another 3, which is 243. And normally I'm just kind of leaving, but I wanted to point out that you can do this relatively, not terribly, by being kind of clever about it and factoring out a 243 from each of those fractions. So I can write this as 2 pi times 243 times 1/2 minus 2/5. And to me, that just feels a little bit less terrible. I think subtracting these fractions is much easier than subtracting these fractions. So might as well finish it off. This is 2 pi times 243 times 1/2 is 5/10. 2/5 is 4/10. Subtract, you get 1/10. So you get 2 pi times 243 over 10. Cancel a 2 here and a 2 here. You get 243 pi over 5. I wouldn't worry too much about anything we did after this step here, right? This is all just the arithmetic part, which I know is important, but is not the important part. So there's an example, one example of volumes by shells. So let me ask, should we also do this one with the disk method, or do you not want me to do that? I'm happy to do it if you guys would like to see it. Yes, okay. So we should get the same answer. So now here's the thing. If you're finding a volume of a region and you're revolving around a specific axis, one way of doing it, like so the shell method in this case ends up being in terms of x. If we use the other method, it'll always be in terms of the other variable. So I already know without having you written anything down that if I'm going to do the disk method here, it's going to have to be with integrating with respect to y, because I'm going to have to use a horizontal strip, and that automatically means with respect to y. So the vertical strip automatically means with respect to x. So yeah. Okay. I feel like I need to like WD-40 up this board. It's getting a lot of noise. All right, so same region. I try and draw it so it's a little bit less big. Pretend this is our region. We intersect at 3, 9 over here. We're going around this axis. And right, if you actually like drew the thing, you'd have a very kind of wide, flat top shape. Right, it would look like this. Here's what the actual thing looks like that kind of. Right, you've got kind of this volume thing going on here. It's got a flat top. But now, instead of using instead of using shells where the strip is parallel to the axis, we're going to use discs where the strip is perpendicular to the axis. So when I rotate that strip around, I get this sort of disc shape where the volume of this disc is the area pi r squared times the thickness, which is dy in this case. So one thing I want to clarify, because this is usually a point of confusion. Actually, before I clarify, let me ask you guys. Have you done any problems, or has he asked any questions where you're rotating around an axis that isn't the x or the y axis? Like, have you had to rotate around y equals 5 or x equals -2 or anything like that? I'm hoping the answer is no. Darn, I was hoping the answer was no. Okay. It's fine if it is. So I guess we should do some of those next. So here's what I'll say. For the disk or the washer method, the radius of your disk is going to be a function, right? It's how far the end of the strip is from the axis, which is going to vary depending on where your strip is located at, right? Bigger radius, smaller radius, but the radius is the function. On the other hand, for the shell method, the radius is just the variable. It's how far your strip is from the axis, not how tall your strip is, right? Here, so let me start saying, here the radius is how tall or how long your strip is. Here the radius is how far your strip is from the axis. It has nothing to do with the height of the strip. So for the shell method, your radius is always something like x or y. Really, it's the distance from your strip to the axis of rotation. So if my strip is located at x, and my axis is x equal to 0, right? The y-axis is x equal to 0. The difference is x minus 0, which is x. Whereas here, the radius of the strip is the function, whatever this function is. It's an important clarification. So in this case, the volume of my disk is pi times my function squared times dy. Where the function was y equal to the square root of x. But again, since things are in terms of y, we have to rewrite this as y squared equal to x. So x equal to y squared gives me a y squared as my radius. Feel free to chime in with questions if you guys have them. So then the total volume is going to be the integral of this volume. Because again, right, just like in the previous one, we were adding up bigger and bigger shells. Here we are adding up disks, right, that are smaller if we go lower. Bigger if we go higher. Right, that's kind of the idea there. Hopefully this picture kind of helps a little bit. Right, you're just adding up all these disks, which means we're adding up all the volumes of the disk, which just means we're integrating. So we're integrating, these disks go as low as 0. These disks go as high as y equal to 3. I totally wrote that point wrong. I'm sorry. That point is 9, 3, not 3, 9. I think I did mess up on the other side. No, I'm right. So we're going from interval from 0 to 3 of pi times y squared squared y, which is going to be pi times the interval from 0 to 3 of y to the 4th dy, which is pi times y to the 5th over 5, from 0 to 3, which is plug in 3 and 3 to the 5th is 243. So we get 243 pi over 5 minus 0. And I do have to say, the arithmetic on this one was way nicer, right? Doing it this way for this particular example was much, much, much simpler than doing this calculation over here. That's not always true. Sometimes the shell method is the simpler arithmetic method. It really just kind of depends. All right, questions about this? And I think next up we will do an example where we rotate around an axis that is something different than the x-axis or the y-axis. Okay. Okay, yeah. So the problem with these volume ones often is that the numbers are terrible, right? You can set it up and it'll be fine, but actually calculating the volume ends up looking pretty ugly. So a lot of times what teachers do on tests is they give you some easy-ish ones to calculate, like where the numbers aren't terrible, and then they make you set up some harder ones, and they say specifically set up, but do not evaluate the interval for the volume of whatever. So what I want to point out is make sure that you read the questions carefully, because if it says set up, but do not evaluate, don't waste your time trying to actually evaluate, because you won't get any points for that. I've definitely seen students on exams I've given find the volume for an interval. I just asked them to set it up, and they did it right, but they didn't get any. There was no value there because they wasted their time doing that when they should have been working on other stuff. Now, I don't know what your test looks like for Mercs, which is next week, I think. On the what day is it on? Let's see. It's on the 20th. You guys still have a little bit more time. Sorry, it's not next week. It's oh no, it is next week. It's a week from tomorrow, I guess. So yeah. But what I want to say is just make sure, right, that you read the questions carefully, and if they say just to set up, that you just set up, you don't actually evaluate. So let's try and find the volume of the solid obtained by revolving the region bounded by. I'm not going to write all the words. Let's see. Now let's see. I have to think of a thing. How terrible do I want it? I don't want it to be that terrible. Let's kind of go the other direction. Sure, I've got one. Let's do that. Yeah, that seems fine-ish. I want to go around that. Okay, sorry guys, I have to make the numbers work for a second. Sure, we'll do this one. This one's usually not too awful. Let's go. I have to make sure it's not going to suck. Sorry. One sec. Okay. Y equal to 4x minus x squared. And then I want this to go through y equals 2x around. Let's go ahead and go around x equal to -1. Yeah, that seems moderately reasonable. So I still think we should graph this. Totally use deadlifts if you want. The thing to think about here is that we have to find where these intersect, right? In the previous problem, we were kind of given most of it. We had to find one thing. Here, you really need to set these equal to each other. So if I set 4x minus x squared equal to 2x, I end up getting, I'm going to subtract this, 2x minus x squared equal to 0. I get x times 2 minus x equal to 0. So I get x equal to 0 and x equal to 2. At 0, both functions are equal to 0. At 2, both functions are equal to 4. Right? So if I plug in 2 here, I get 4. If I plug in 2 here, I get 4. So these are intersecting at 0, 0, and 2, 4. And the y equals 2x is just a straight line. And y equals 4x minus x squared is a downward open parabola. If I factor out the x, like y equals x times 4 minus x, I see a parabola with x-intercepts at 0 and at 4. where the vertex actually is at this point where they intersect. So it looks like this. It kind of looks like that. So here's the region. And I'm revolving, not revolving around the y-axis, revolving around the line x equal to -1. Okay, so typically you can use either method, washer or shell, or disk. This is definitely going to, if we were going to use disk or washer, it would definitely be washer because our region is not flush with our axis of rotation. So how do I decide which I want to use if I'm not told? Well, here's the thing. I kind of think about which kind of strip I want to draw. Do I want to draw a vertical strip or do I want to draw a horizontal strip? Here it seems like either one would be fine, right? If I draw a vertical strip, I'm just going to, right, like, so what I'm really trying to say and having a hard time is you want the ends of your strip to always be the same function, meaning if I draw a vertical strip, I'd like the top part of the strip to always touch the same function and the bottom part to always touch the same function, and it will. The same would be true here if I was going to draw a horizontal strip. Right, my horizontal strip, the right side would always touch this line, the left side would always touch this parabola. So since neither of those is a problem, I can pick whatever I want. When all else fails, if I'm going to pick a strip that's going to keep me using the variables I've already got, meaning my functions are written as functions of x. I would prefer not to have to change things to be in terms of y unless I had to. Since I don't have to, I'm going to draw a vertical strip where I have a dx so that I keep things as functions of x. So I'm going to draw a vertical strip. Let me use a different color here. Let's use green. So I'm going to draw a vertical strip. Okay, so I've got my vertical strip. I've got my vertical axis of rotation, meaning I have to use which method? The shell method or the washer method? Remember the rhyme. Yeah, exactly. It's the shell method because our strip is parallel to our axis of rotation, right? They're both oriented the same way. So this is the shell method, right? So we're going to be using the shell. And then I'm going to say the volume of my shell is going to be, and I'm just going to write the usual 2 pi r times h times dx, where I have to fill in what the radius and the height are. Okay, so here's the thing. I'm thinking of this vertical strip at a distance of x from the origin, right? This distance here, which I know it's kind of hard to see, so I've drawn this. But that distance there is x. But that's not my radius, because I'm not going around the y-axis. My radius is actually that distance there, the distance from the strip to the axis of rotation. And here's the easy, well, maybe easy thing about it. The radius is just wherever your strip is, well, I should say it's wherever your strip is minus wherever your axis of rotation is, if the strip is further right. Or if my axis is over here, which I'll do in a second, it'd be the axis minus the strip. So x minus minus 1 is my radius. That's my radius. And my height is just the height of the strip, which is the top function minus the bottom function. So that's going to be the top, which is the parabola, so 4x minus x squared, minus the bottom, which is y equal to 2x. And as you can see, this is going to be kind of gross to actually calculate, right? Which is why I would definitely give this problem as a setup, but do not evaluate kind of question. We can still evaluate it, but I'm just warning you, these shell, really any volume where you're going around an axis that's not the x or the y axis is usually going to be a little bit less nice. So there's what we've got. So we're going to find the total volume by integrating 2 pi times this mess here, x plus 1 times 4x minus x squared minus 2x simplifies to 2x minus x squared. And our limits of integration, we already found them. And from x equals 0 to x equals 2. Getting a phone call from a Davis number. Probably just spam. All right, so that's our setup. We can go ahead and calculate it, but again, it's going to be a little bit gross. A couple things before we calculate. So 2 things. Once again, here is the attendance and tutoring, and then also here is the link to the Zoom office hours this afternoon from 2:30 to 3:30. I will also post that link in Canvas in an announcement probably. So if you don't get it here, but you want to come, you can always you can do that. We were integrating a thing. Don't forget the 2 pi. It's easy to forget the 2 pi. Let's see. X plus 1 times 2x minus x squared. Ooh, that's nice. I do want to remind you, you have to multiply this out before you integrate. You cannot integrate these 2 things that are factors independently. So, I mean, I guess you could do something weird like using integration by parts for this. You should not do that. It's a bad idea. So multiplying this out, I get 2x squared minus x cubed plus 2x minus x squared. And although you could integrate this as is, I would probably rewrite it, simplify it, combine the 2x squared and the minus x squared to get minus x cubed plus x squared plus 2x. And now it should be fairly straightforward. This one actually isn't that bad in the realm of volumes. I'm going to get, let's see, minus x to the 4th over 4 plus x cubed over 3 plus 2x squared over 2, which is just x squared, from 0 to 2. I can see that when I plug in the 0, they're all going to be 0, so I'm just going to worry about plugging in the 2. I'm going to get minus 2 to the 4th, so be careful. It's 2 to the 4th and then the negative of that. So it's minus 16 over 4 plus 8 over 3 plus 2 squared is 4. This is minus 4, that's positive 4, they cancel. So 8 thirds times 2 pi, which is 16 pi over 3. Not too terrible. All right, let's see what time is it. Okay, we got like 17 minutes still. Should we do another one of these, or is there something else you guys would like to see? I can think of something that I would rather not do, but if you guys ask for it, I will totally do it. You guys are like, what could you be talking about? The thing I don't want to do, but I'm happy to do if you guys want me to, is one of the volumes where you have like the slices, right? Not shell, not disc or washer, but the volumes by slicing. Would anyone like to see a volume by slicing? Okay, I figured you guys would. I just didn't. It's just there's always they're the worst ones for me to draw. They're hard to draw. Sarah had a good idea, which maybe I'll try and implement. I might need a pair of scissors though. Yeah. So let's see. Oh, she said I don't think I have any colored paper though. Do I have any colored paper? No, I do not really have any colored paper. Oh well, next time. So let's see. And I always have a hard time phrasing these ones, so let me look. Sure. You know what? I've got a book with all kinds of problems in it. Let me look at it real quick. Let me grab one here. Volume using cross sections is how it's often phrased. You know, and I might just do one that's actually from this section so that we can kind of, yeah. No, that's a terrible one. I want to do that. There's a nice picture over here. Ooh, that looks stupid. Okay, so let's do this one, even though it looks awful. So here's the setup. I'm going to try and draw a picture, but then I'm also going to show you the picture in this book. So the solid lies between planes perpendicular to the x-axis at x equals -1, x equals 1. Okay. Solid lies perpendicular, or sorry, between planes. And this is phrased already stupidly. Perpendicular to the x-axis. At x equal to -1 and x equal to 1. So what they're trying to say with this, so here's my x-axis, and here's my y-axis. We're doing it kind of in this 3D sort of way. And in between planes at x equal to x equal to 1. So I've kind of got this, right, I've got this big old kind of barrier here at x equal to 1, and also at x equal to -1. Right, so when I say a plane perpendicular to the x-axis, I mean like this, the x-axis is kind of cutting this big plane here. And then the shape, so the cross sections perpendicular to the x-axis are circular discs. Cross sections are circular discs. Whose diameters run from y equals x squared to y equal to 2 minus x squared. Okay, so I'm going to draw those in just the regular xy plane. So here's y equals x squared. And in fact, let me draw this a little bit more nicely than I usually would. There's y equals x squared. And then opening downwards, y equal to 2 minus x squared has a vertex here, and does this, and then this, and this kind of deal. So what we're saying is the diameters of our circles are here, right? And then the circle kind of pops out at you, right? So you've got this circle that's doing kind of this. This is where my drawing skills are terrible. So what's happening, if we try and draw it over here, okay, help, pray for me. Here's my parabola opening that way. Here's my red parabola opening that way, which already looks awful. And here's my diameter, and here's my circle that's there. And hopefully you guys don't think that's too awful. Let me show you the picture in the book, because I think that might help us a little bit more. So, okay, so we're looking at this one right here. Hopefully you guys can kind of see, oh yeah, you've got these parabolas, and the diameter of the circle is given by the being between those two parabolas. So I think that might kind of help, hopefully. All right, so there's the setup. How do we actually calculate this thing? Well, okay. So here's what we're trying to do. We know that we are integrating from -1 to 1. Right, so we're going to do the integral from -1 to 1. And we know that the area of the cross section we're going to write as a of x. That's how we typically do this. You say, okay, we're going to integrate it from here to here, or wherever to wherever, and we have to find the area of the cross section. Well, we know what shape it is. The cross section is a circular shape. So that's going to be a little bit more easy to figure out. That's going to be integral from -1 to 1 of pi times some radius squared. So what we actually have to do is we actually have to figure out the radius of that diameter. Okay. I'm going to erase some of this because I need more room. So let me draw this picture again. So here's my strip. And I'm trying to figure out what the radius of this strip is. So actually I'm trying to figure out what this length here is. Okay, it's actually not as bad as it looks. And well, maybe you guys can't see how it looks. It's just going to be half this length, right? The radius is half the diameter. The diameter is the length of that strip, which is just the top function minus the bottom function, which is 2 minus x squared minus x squared, which is 2 minus 2x squared. And then the radius is just half of that, which is 1 minus x squared. So that's how we find the radius here. So then our volume would be the integral from -1 to 1 of pi times this radius squared. And then the rest is not too awful. We might as well do it. I think someone asked something. Well, let me actually get there before I start. If I'm going to integrate this, let's see, pi times the integral from -1 to 1. Then multiply this out. It's 1 minus 2x squared plus x to the 4th. And I'm pretty sure someone asked before if we can do the thing where we double it and go 0 to 1. And we can, because this is an even function, right? All the powers of x are even. So I can write this as 2 pi times the integral from 0 to 1 of 1 minus 2x squared plus x to the 4th. So I end up getting 2 pi times integrate, I get x minus 2x cubed over 3 plus x to the 5th over 5 from 0 to 1. And I can plug in, okay, let's see, 1 minus 2/3 plus 1/5. And we could simplify that, but I don't think we should. So that's one example of a question like this. I think we should do one more. But I will say generally, these are not my favorite. Not that they have to be, but like, they just kind of always feel, I don't know, they feel weird. So typically, the shapes that you might be asked to deal with as cross sections can be circles, semicircles, squares, triangles, or triangles as people usually say that, equilateral or other. Let's see, let's look at another example. That seems awful. Sure, let's do this one. So let's say the base of my solid, and this might turn out to be actually super duper awful. Let me make sure this isn't as terrible as I think it is. All right, base of the solid is the region between, y equal to, it seems dicey, oh well, 2 square root of sine x, and y equals 0, and the cross sections are sure, let's go with squares. With base that is, yeah, the base is parallel to the y-axis. Okay, so let's take a look at this. So I'm going to draw this, and again, I'm just using kind of my knowledge of sine. I know the sine of 0 is 0, and the sine of pi is 0. And I think it does say from 0 to pi. Yeah, it does say from 0 to pi. And it's just going to kind of, it's not going to exactly look like a sine function, but it's going to kind of look like something like that. Sure. And so the idea is we're going to draw squares that are parallel to the y-axis that are sticking out of, right? So we've got like a square, right? That's kind of the idea there. Or if I tilt, so if I tilt this, if I rotate this kind of back, right? If I do it like that, Now my shape kind of looks like, well, it looks stupid. Sorry, this is always kind of the real test of my drawing skills. So there's my same shape, but tilted back, and now my squares, you know, look, not parallel. So here's my square. And here's a square or a rectangle. So the shape kind of does this thing. So some weird looking taco. Anyway, how to find the volume? Well, so we're going to do the integral. So of our area. Yeah, I should do this pen break. Well, we're going from 0 to pi. And the area of one of these squares is just the height of this function squared, right? It's this length times this length, but this length, the length of the side of the square, is just a function. And that's it, right? There's nothing else to do there. There's no pi. Well, there's a pi. Right, if instead of it said it was like a semicircle, instead of doing 2 root sine of x, I would have taken that length, I would have cut it in half for the radius, and I would have done pi times the radius squared. In fact, let me set that one up as well, just to show you. So if instead they were semicircles, so like this, right? So we had semicircular cross sections. My volume for the semicircles, what time is it? Oh, almost on time. Okay. Would have been the integral from still 0 to pi, but now my cross section, instead of being the length squared, it's going to be 1/2 the length for my radius. So be pi times my 2 root sine x over 2 squared, right? Where this thing in the parentheses here, that is the radius of the semicircle. But I forgot one thing. This is pi times the radius squared, which is the area of a circle. Right? Pi r squared is the area of a circle. I need 1/2 pi r squared to get me the area of a semicircle. So that's what these both look like. This one is not too terrible. 2 squared is 4. Square root of sine, square root of sine. You integrate sine, you get negative cosine. From 0 to pi. You plug in pi. Cosine of pi is -1, so you get 4 times -1. Minus 4 times plug in 0. Cosine of 0 is 1, so you get -1. So you end up with, let's see, 4 plus 4 is 8. Here, it would be very similar. It seems like it should obviously be less volume. So let's see, here I end up with 1/2 the integral from 0 to pi of these two's cancel. Square root of sine squared is just sine. So it looks like this is the same as that. It's just 1/8 as much. Let's check. We get 1/2 times negative cosine of x from 0 to pi. You get 1/2 negative cosine of pi minus negative cosine of 0, which ends up being 1/2 times negative cosine of pi is -1, plus cosine of 0 is 1, and 1/2 of 1 plus 1 is 1. All right, so there's a couple examples of those. The idea really is whatever the length is from, like whatever the length of your base is in terms of your function, you have to take that length and manipulate it to give you the area. So if it's a square, you just take that length and square it. If it's a circle, you take that length, cut it in half, that's your radius, and you do pi times your radius squared. If it's a semicircle, you do half of that. If it's an equilateral triangle, we are sad because they're the worst. But there is a formula for that, and we can talk about that next time. Again, I have office hours this afternoon from 2:30 to 3:30. I will remind everybody, or maybe not We'll let everybody know that, why can't I find the link to the office hours? You know, I posted it once or twice here. Well, let me find it again, sorry. Let me do this. So here is the office hours link. You all are welcome to attend. There it is right there. That was just above 2:30 to 3:30. I want to say, I also provide those office hours for my stat students, and none of them have been coming, but I do kind of said that they would have priority. So if any of them do show up, I will probably answer their questions first, or at least one of their questions first before getting to you guys. But again, please feel free to come. I'll see you all or not at 2:30, and take care. All right, I'm gonna make some videos this afternoon about more things. All right, that's all. I'm just rambling. Talk to you guys later.